Today, we are diving into a Nobel Prize that's not just for finding something new, but for inventing a whole new way to build. I mean, literally, a way to construct our world atom by atom. We're talking about the power to design materials that could genuinely solve some of humanity's biggest, toughest problems. So, let's get into it. Just take a second and think about that. What if you could sit down and design, from scratch, a material that could pull fresh drinking water straight from the desert air? Or what if you could build another one specifically to scrub the carbon dioxide that's warming our planet right out of the atmosphere? I know, it sounds like something straight out of science fiction, right? Well, it's the incredible reality behind this year's Nobel Prize. And here it is. The 2025 Nobel Prize in Chemistry has been awarded for the development of something called metal organic frameworks, or MOFs for short. And believe me, this is a technology that is absolutely poised to change, well, just about everything. So, what in the world are these frameworks? Look, this is not your typical chemistry, just mixing stuff in a beaker and seeing what happens. Nope. This is molecular architecture. It's a completely revolutionary way to build matter, piece by piece, from the ground up. Okay, let's just break the name down because it tells you everything you need to know. A metal organic framework is a crystal, and it's built from two main parts. First, you've got your metal ions. Think of these as the cornerstones, or the joints in a structure. And then you have organic, carbon-based molecules that act as the linkers, the long poles that connect all those joints together. Probably the best way to picture this whole thing is to just think of Legos, but, at the atomic scale. You have all these different types of bricks, the metals and the organic linkers, and you get to choose exactly which ones to use to build a structure with the precise shape, the perfect size, and the exact properties you're looking for. It is, without a doubt, the ultimate toolkit for chemists. So how do you actually build with these atomic Legos? Well, this is the really cool part. It's a surprisingly simple, almost elegant process. It's all about self-assembly. Let's walk through the steps right now. All right, step 1. You start with your cornerstones. These are positively charged metal ions, things like copper or zinc. They're going to act as the central hubs, the points where everything else is going to connect in the final structure. Step 2. You bring in the linkers. Now, these are long organic molecules that are specifically designed to snap onto those metal ions. So think of them like the beams or the struts that are going to span the distance between all your cornerstones. And now for step 3. This is where the magic really happens. You just mix them together. That's it. The parts spontaneously find each other and connect into a perfectly ordered, repeating crystal structure. They literally build themselves. No tiny robots, no complicated machinery. The chemistry does all the hard work for you. And the result is what's so incredible. You get this structure that is mostly empty space. It's unbelievably porous. The Nobel Committee even described it as being like a diamond that's filled with cavities. And the internal space is just vast. To give you some perspective, a single gram of a MOF that's about the weight of a paperclip can have an internal surface area the size of a football field. It creates all these perfect little rooms, just waiting for chemistry to happen inside. Of course, a revolution like this doesn't just happen overnight, and it's not the work of one person. It was really the work of 3 key pioneers, the architects who laid the foundation for this entire field. The story really kicks off back in 1989 with Richard Robson. He had the brilliant initial idea, but his first creations, well, they just weren't very stable. Then Susumu Kitagawa came along and showed that these frameworks could be dynamic, that gases could actually flow in and out. And finally, Omar Yaghi basically cracked the code, figuring out how to make them incredibly stable and, crucially, how to design them on purpose to do specific jobs. And this is just a perfect example of how science really works, right? You had Robson, who sparked the whole idea, then Kitagawa, who showed what was possible, and then Yaghi came in and turned it into a robust, practical tool that chemists all over the world could actually pick up and use. Every single step was absolutely crucial. Okay, so we've met the architects, we understand the atomic Legos. Now for the big question. What can we actually build with these things? This is where it gets really, really exciting. And hey, don't just take my word for it. The chair of the Nobel Committee for Chemistry himself said that the potential is enormous, and that we're talking about previously unforeseen opportunities for custom-made materials. That's a pretty big deal. Just get a load of this list of potential uses.
We're talking about harvesting water from the air, capturing CO2 to fight climate change, storing dangerous gases safely, and even cleaning up those toxic, forever chemicals from our water supply. These aren't just small improvements. These are potential game changers for some of the biggest challenges we face as a species.
Let's just zoom in on two of these. For water, you can literally design a MOF where the pores are the perfect shape and have the perfect chemical properties to grab onto water molecules, even when there's very low humidity. Then you just add a little bit of heat and it releases the water. For carbon, you can design a totally different MOF, whose pores are a perfect fit for a CO2 molecule, trapping it while letting all the other gases in the air just pass on by. It's precision engineering on a molecular scale. And, this isn't just a theory or some lab curiosity. Since these breakthroughs, chemists have already created tens of thousands of different MOFs. There is an absolute army of researchers out there right now designing brand new frameworks for countless different uses. The creative explosion has already begun. So that really leaves us with the ultimate question, doesn't it? For the very first time, we have the blueprint to build materials from the ground up, to solve our most pressing problems. We have the atomic Legos. The only question left is, what do we build first?